All right, so we are just going to take this problem from the top, do it from top to bottom as if it was on the homework tonight, and answer all the pieces of it. And we're just going to do it in the order that it asks us to do it on the homework. So the first thing we want to find is the y-intercept. Now, you technically could factor first. That would work. I like to find the y-intercept first, though, because notice if I plug in, well, you'll see in a second, when I plug in, a lot of stuff cancels when it's not in factored form, which in my opinion is a little easier, but personal preference, that's how I do that one. So a reminder that we find the y-intercept. The y-intercept is where a function crosses the x-axis or the y-axis, right? So if we were to, sorry, I was on eraser. If we were to draw this, this is my function's y-intercept. That ordered pair is 0, whatever the y value is, right? X is always 0. So if we know that our y-intercept, it's an ordered pair, is 0, something, we can always find that other point by plugging 0 into our function, plugging 0 in for x. So 2 times 0 squared minus 11 times 0 plus 12 divided by 0 squared minus 5 times 0 plus 4. Okay? That, again, this is why I like doing it in non-factored form. All this stuff that's being multiplied by 0 cancels. So we're just left with 12 over 4, which is 3. So my y-intercept is 0, 3. And remember, you have to write that as an ordered pair because it's a point on your graph. And I need to know that it's a point, not an equation. Okay, so that's our y-intercept. Next up, we've got a factor. We want to factor for two reasons. One, we need to see if there's a removable discontinuity. We need to see if there's a hole anywhere. The second reason is it makes finding the other intercepts, the other asymptotes, a little easier. So I'm going to factor these separately, and then I'll put them on top of each other and we'll see if anything cancels. So the denominator is actually pretty easy, right? Because it's a leading coefficient of 1. So it's just a matter of asking myself, what multiplies to positive 4 and adds to negative 5? And it's going to be x minus 4 and x minus 1. Okay? The numerator is a little trickier, right? Because it has a leading coefficient of 2. So we have to do the AC method. Multiply a and c together, we get 24x squared. So we're looking for what multiplies to 24x squared and adds to negative 11x. So let's see. I've got 6 and 4. That's not going to work. And notice, I know they both have to be negative because they're multiplying to a positive. They're multiplying to a positive number, but adding to a negative. So 12 and 2 is not going to work. 6 and 4 is not going to work. It's got to be 8 and 3. So then I can factor by group. I wrote 8 like 5 times. I did not mean to do that. I was just a big fan of 8. 8 and 3 is what it is. So then I can rewrite, spread it out, right? I know negative 11x, is the same thing as negative 8x minus 3x. So now that I have that, I can then factor by grouping, right? Look at this group. I can take out a 2x. I'm left with x minus 4. Look at this group. I can take out a negative 3, and I'm left with x minus 4. So now I factor out an x minus 4, and 2x minus 3 is what's left over. So now I have my numerator is x minus 4. X minus 4 times 2x minus 3, and my denominator is x minus 4 times x minus 1, right? And we can see that x minus 4 divided by x minus 4 cancels, so our final factored form is going to be 2x minus 3 over x minus 1, and that's what we're going to use moving forward to find our other pieces. But keep in mind, I need you to show me this work, right? You can't just write 2x minus 3, x minus 1, and call it a day. I need to see all of these steps. So now that we have that, we can keep in mind that function, but also our removable discontinuity is what we can find now. So we canceled x minus 4. And what that means is if I were to plug 4 in to my old function, well, that would be 2 times 16 minus 44 plus 12 over 16 minus 20 plus 4, and that's going to be 0 over 0, right? That's problematic. When I plug in 4, that's a problem. That gives me alarm bells. So I'm not working with this function anymore. I'm working with the function f of x equals 2x minus 3 over x minus 1. But I can't just pretend like the other, function didn't exist. We still have to take into account that we canceled out the negative 4. And the x minus 4, the way we do that is by finding the point on this new graph where x equals 4 would have been. Right? All the other numbers, if we were to plug 5 into this and 5 into this, it'd give us the same answer. If we were to plug 8 into this and 8 into this, it'd give us the same point. Negative 3, it's going to give us the same point. The only point that's different is the 4. So we need to find that point so we can say, oh, there's a hole there. The graph doesn't actually touch there, right? When we actually end up graphing these, you'll have your graph. When you get to that point, you'll do an open circle, and then you'll keep going to show that everything but that point is the function. So how can we find the ordered pair? Just plug in for 4. And again, we have to plug into our new function because our old function would give us, 0. So that gives us 8 minus 3 over 4 minus 1, which is going to be 5 over 3. So now we know our removable discontinuity, which is the same thing as a hole. Those mean the same exact thing. Our hole in our graph is going to be at 4, 5 over 3. So when we go to graph this, we're going to put an open circle at 4, 5 over 3, right? And if you were to graph this on Desmos, it would say 4, undefined, because it's undefined there. That's not an actual point on the graph. This is a hole, but we have to account for it in our sketch of the graph. So we draw that hole in. Okay, so now, again, this is the function we're using moving forward to find all of our other stuff. So vertical asymptotes are where the function's undefined. And where is a fraction undefined? It's undefined when the denominator is 0. We can't divide by 0. So to find my vertical asymptote, all I do is set my denominator equal to 0. Now in this case, because we canceled things, we only have one number in the denominator, but I want to make sure it's clear that you can have multiple vertical asymptotes. You can have 3, 2, 1. It just depends on how many factors are in the denominator. So say there was something else here. All of these would be vertical asymptotes. You can have multiple. In this case, though, we just have one, and it's at x equals 1. Okay? And asymptotes are a line. It's a line we sketch into our graph, so you've got to make sure that you you write it as an equation. All right, then we can find our x-intercepts. Now, we know x-intercepts, it's where the function crosses the x-axis, and you can have multiple. You can have 1, none, 5, 10, whatever. You can have as many factors as there are in the numerator is how many x-intercepts you're going to have, right? So if the x-intercept is where it crosses the x-axis, that means y is 0. So we set, and f of x is the same thing as y, we set the function equal to 0 to solve for the x-intercepts, right? Because we're looking for the x value when y is 0. Now, we would multiply both sides by the denominator, so really what you're doing is you're setting the numerator equal to 0. We set the numerator equal to 0 and solve that, right? Because the denominator is always going to cancel. But you can also just remember, like if you there's no memorization here if you genuinely understand what an x-intercept is, right? If you know that an x-intercept is where the function crosses the x-axis and where y is equal to 0, then you don't have to memorize that you set the numerator equal to 0. You should just be able to use this fact to solve it. So we add 3. Add 3. 3 equals 2x. X equals 3 over 2. But then remember, this is an ordered pair. It's a point on my graph. So for vertical asymptotes, we write it as x equals 1 because that's, a line through x equals 1. But this is a point on our graph. So we have to write it as 3 over 2 or 1.5. I don't care. Comma 0. You have to write it as an ordered pair. I do care about that because it's a point on our graph. And last but not least, we need to find our horizontal asymptote. So to find the horizontal asymptote, you need to look at the degree. The degree of the numerator and the degree of the denominator. Now, remember from class today, the degree is the highest exponent, right? So if we had something like 5x minus 4x cubed plus 7, the degree of that is going to be 3 because the highest exponent is 3. So if we look, both of these don't actually have an exponent. They're linear, so it's x to the first. So the degree of our numerator and denominator are both 1. Well, if we flip through our cases of what we do for horizontal asymptotes, when the degree of the numerator equals the degree of the denominator, you take a ratio of the leading coefficients. So remember, leading coefficient is the coefficient of the term with that, highest degree. So like in this case, the leading coefficient would be -4. Well, here, the number with the variable of the highest degree is a 2. And then here, there's nothing, which means it's a 1. So our asymptote is going to be 2 over 1, which is 2. Again, this is an equation, so we have to write it as such. But it's a horizontal equation, so it's y equals. And then we're done. Later we'll graph it. We'll use all of these pieces to, throw a graph on the page. But for now, we have enough information. We found all the characteristics.